Now I will present our research work, sliding loop-back window-assisted data chunk rewriting for improving deduplication restore performance. I'm Zhichao from University of Minnesota, and you know it's very cold there. But we don't have such a strong wind, right? Yesterday, I nearly blacked out on the plane. So this project is done with other 4 students from Ocean University and the North-South China University of Technology. And David is our advisor. I will first introduce about dedupe and then go through those topics one by one. So let's look back to the old school things, what is dedupe and restore. So actually for the dedupe process, usually for a backup company, they just form a byte string from a backup or snapshot, and then they cut the byte string into chunks while using like the CDC or fixed size chunking algorithm. Then you will have the chunk itself. By using a hash function like SHA-1 MD5, you'll get the chunk ID represented by the fingerprint. Then you will have a database tells you whether this chunk is in the system or not. If that's a new chunk, you will store it in usually in a container because we want to benefit from the sequential write or read from the HDD in the system. And then we need the metadata tells you, okay, in the future, how can you restore the original data back to its state? So the recipe will tell you, okay, you fetch this sequence of the data chunks, and then you will get your chunk out. So we continue this process and generate the containers to the storage and get the new chunks from the byte string. If the chunk is found in the system, we don't need to store it again. We just need to append the information to the recipe. But in the future, if you need the original data, you need to restore them back. So there are a lot of papers discuss about how to restore them back quicker by using like different caching algorithms or different rewrite algorithms. So what they did is usually, according to the recipe, the content, it will tell you, okay, you need to fetch this data chunk 10, and then you look through the cache space, see whether you have the chunk or not. If you don't have it, you fetch out the whole container to the memory, and then feed to the assembly buffer. After that, you may have some mechanism to refresh the cache. And next, after the assembly buffer is full, the data is returned to the user. So the step will continue. Sometimes if the chunk is in the cache, you will have a cache hit, so you don't need to have a very expensive storage I/O for the 4 megabyte or 8 megabyte size container. So just a memory copy to the assembly buffer. So that's roughly the process of the restore. You can see now caching is a very good way to do the restore and help us to improve the restore performance. But is it a very perfect design? The answer is no. Let's look at this example. For those 4 chunks, they are from different containers because the system runs for some time and the recipe referencing to the old containers. In this case, if we want to restore them back, we need 4 container reads for those 4 chunks. That's very expensive. And actually, if you look back to the past and look to the future, you find out, okay, other chunks are irrelevant to the current restore. So your container reads cannot benefit the future restore process. So caching loses power, actually. And then some people think about, okay, let's do some trade-off. If we can store those scattered or fragmented data again, then we can just have 1 container reads and cover all of them. So like those chunks will be stored together with the unique chunks in the container. And in the future, you just need 1 container reads and fetch all of them out. But the downside is you need to pay for the price to the space because you store those duplicated chunks again. And there are a lot of works about how to do the rewrites, like the chunk fragmentation level paper and the history of rewriting algorithm, the container capping one. But rewrite is still challenging. The first one is we make the trade-offs between the duplication ratio and the restore performance. So how to find out a good trade-off is a problem. The second thing is actually different from the restore process. You have the recipe, which tells you, okay, which chunk will be used in the future. But now you are in the deduplication process. You don't know what will be in the future. So the information is limited in this process. So that's difficult to make a very precise or good decision for the rewrite. The third thing is we cannot separate the dedupe process with the restore process. In the future, when you restore it, maybe the chunk is already in the cache, but you think we should rewrite it. In this case, you are wasting your space. So for the next step, I will introduce one important rewrite scheme. We call that container capping. So this is a paper from HB Lab and published in 2013, FAST. Personally, I love this scheme because it's very simple and effective. Let's briefly look at what they did. First, they just cut the whole byte stream into segments. Usually that size is 5 containers, like 20 megabytes. It will have about 5,000 chunks inside it. Then they identify the chunks, whether that's a new chunk or that's existing chunk. Like the colored one, that's the chunks from different container. If that's a new chunk, we store them into the active container, and then they sort all the old containers referenced by this segment from high to low according to the referencing count, which means if this container has higher referencing count, we rank higher. And then they set up a cutting point called capping level. In this case, that's 3, which means, okay, for the containers ranked higher, we will still use them in the recipe. We reference them. For those lower ones, we rewrite them to the new container and referencing to the new containers in storage. By doing that, the good thing is when you restore the whole segment, at most, you only need to read out 3 old containers plus several active containers generated in this process. So they have a guarantee for the higher bound on the container rates. But this is not perfect. They have some limitations. So we can see in this game, they made a cut at some position and do the calculation inside the segments. Is this cut a good way? We don't know. The second thing is they set up this capping level. In their paper, they said maybe 20, 30, but we don't know which one is a good capping level. And also for different segments, a fixed capping level may not be good. It should be various according to the distribution. Also, even we rewrite those containers with fewer referencing counts, but we cannot guarantee the duplication ratio. So that's the 3 limitations of the capping scheme. First, they use a fixed capping level. First, like I said, they do sorting on the reference count, and then they just pick up the containers with higher referencing count and store them and pick up the right side one to be rewritten because they have lower referencing count. If we read out them in the future, that will cost a lot. So that's the capping, but from the 2 examples, we can see maybe we can move the capping level to the left or to the right. For this one, actually, we can rewrite fewer chunks and just tolerate 3 more container rates. For the right side one, we can move to the left because we can tolerate more rewrites and then save on the container rates. The final result is we still have about 20 old container rates, but we rewrite fewer of these chunks. So that's the first limitation. For the second one, actually, we know that how to cut the segment, right? We can move it forward, backward, then the rewrite decision will be different. So how to find a good way to make the cut? That's a problem. The third thing is about the caching. In the restore process, some of the chunks will be in the cache, but according to the segment sorting, they may be rewritten in the future, like this example. Actually, those brown chunks are covered by the cache, but according to the segment design, we still rewrite those 2 blue chunks and those 3 brown chunks in the segment. So they may rewrite more. So based on those three limitations, we make two new designs. The first design is totally based on the capping and make small changes. For the second one, we propose a totally new approach to do the rewrite. The first one is called the flexible container reference count-based design. So from capping, we know that we cut it from the ranking, but now we cut into a horizontal direction, which means that is the referencing count threshold. So if we have a very high threshold on the referencing count, which means we will rewrite all of those chunks below the threshold. In this case, we'll have fewer container rates. But if we set the threshold lower, which means we rewrite fewer chunks, but we need to tolerate more container rates, the problem comes out, okay, in this case, how can we set up that the container reference count threshold for each segment that varies according to the distribution of the chunks in that segment, right? So one way is based on the user requirement, you set up the higher bound and lower bound for the reference count threshold, and then you can adjust between them. So for the higher bound, that assures that you can rewrite at most how many chunks in it. And for the lower bound, that ensures you can have at most how many container rates. Those two bounds will tell you, okay, what's your adjustment space. So like in this example, we have 7 containers referencing one segment. And then maybe user said that, okay, I can tolerate at most 3% of the deduplication ratio reduction. According to this ratio, we can estimate how many chunks can be rewritten at most in each segment. We have that number, then we can calculate, okay, that's a higher bound of the threshold. We cannot rewrite more than this threshold. Then the user may say, okay, I need ensure for each segment we read out at most 20 or 30 containers, old containers. Then we have a lower bound on the threshold. So from top to low, that's the number of the container rates will happen in this segment. So with those two thresholds, we can pick up the FCRC threshold between those two bounds. And one more good news is, if we choose the threshold in between, actually, we rewrite fewer chunks than the higher bounds, and we will have fewer container rates than the lower bound. So those credits can be accumulated to the future restore process, which means in the future, maybe the two bound can be moved up or moved down. Then we have more space to adjust the threshold. So that's the credit accumulation. So based on the whole process, starting from first segment to the following one, we will adjust the boundary according to the user requirement and also according to the real container rates and data chunk rewrite. Those will make good trade-offs between the space saving and the restore performance. So is this scheme good enough? No, because it does not solve the fixed counting boundary issue in the capping. So we know that we don't know how to cut the segment is a problem, especially for the chunks near the boundary. They have less information for the future or for the past. So a good solution is we make the decision, we make the cut everywhere. So we have a sliding window, move container size chunks one by one, then, which means we cut it everywhere. And then each chunk will be evaluated with the same amount of information for the past information and the future information. So we'll know two sides of the look-back window information for each chunk to make the rewrite decision. The third thing is we have the look-back window, which means some of the chunks may be rewritten in the future. We cannot make the decision directly. So we need to have candidate cache to hold those chunks that cannot make the final rewrite decision. And we need the recipe cache to tell you, okay, those chunks are in the window, and if they are moved out, we will finally drop them out. This is the architecture of our new design, and you can reference to the paper and see the details. And inside this architecture, you can see the recipe cache size is exactly as the lookback window size. And those chunks that might be rewritten in the future are in the candidate cache. Once we make the rewrite or non-rewrite decision, we drop them from the cache. The third thing is we consider the cache effective range during the rewrite. So what is a cache effective range? It means we can estimate, after I have the container rates, for how many chunks restore, it will still be in the cache. In that case, we don't need to rewrite. For the FA, which is a restore caching algorithm proposed in HB, the FA size is cache effective range. And if we use a chunk-based cache, we can estimate the average caching effective range and cover a bunch of data chunks. So let's look at the overall example of this LBW design. Suppose that the LBW size is 2 containers, which means 8 chunks. And then the cache effective range is 3 containers, 12 chunks. And we can make the rewrite decision based on, OK, if this chunk from 1 container, the referencing count is lower than 2, then we rewrite this chunk. So in this example, the white one is a unique chunk, and we store them in the active container. Then the loopback window moves. Now we fill in the recipe cache with the entries that still reference to the old containers. Next step, we check the chunks at the tail of the recipe, those brown chunks and the purple one. We see now, OK, the purple one, actually, there's no other chunks from the same container in the future, which means it's the only chunk in this range, and it will trigger the container race in the future. So we will move it to the active container. At the same time, for those blue ones, there are only 2 of them appearing in the lookback window. We add them to the candidate cache because we don't know whether in the future other chunks from this blue container will appear or not. They may appear, then we drop it from the candidate cache. If they do not appear, which means in this range, we only have 2 chunks from the blue container, we need to rewrite them. So now the purple one is rewritten to the active container. Then we will check the brown chunks from the container read point to the cache effective range covered space. If the chunk is not covered by this cache effective range, we need to rewrite them. So we can see all of them are covered. So we don't need to rewrite any of the brown chunks. So for the next step, we drop the cache and move forward. Then new recipe entries are added to the recipe cache. Now we see 1 blue chunk, 2 blue chunks, and 1 green chunks. So we know, OK, for those 2 blue chunks, actually, they have other neighbors from the same container in the short future, so we don't need to rewrite them. We can tolerate the container rates for the blue container. But for those green ones, this is the only one appearing at this moment, and we look back to the past. OK, there's no other green chunks appearing before, which means it's well as possible 1 container race will be triggered at this moment by this chunk. So we add it to the candidate cache. And now we know we have more blue chunks, so we don't need to rewrite them. But let's look at this brown one. Even we have container rates for the brown chunk before, but this chunk is already out of the cache effective range. So we need to rewrite it because it is very possible at this moment, 1 more container rate will be triggered by this brown chunk. But maybe in the future, there will be more brown chunks comes out, so this container rate is tolerable. We can still rewrite, do not rewrite it. This is a whole story about the loopback window. So it looks like it is simple, and whether it works or not, we need to have an experiment to test them. So this is the rewrite policy. What we did is we emphasize on the rewrite decision, make it as early as possible. And the next thing is we consider some locality things and made the adjustment on the threshold. So let's move to the evaluation. Actually, for a lot of rewrite paper, people care more about the speed factor, which means in average, one container rate can contribute to how many original data restore. If the speed factor is 1, which means you read out one container, which is 4 megabyte size, you only restore 1 megabyte original data in average. So the speed factor is higher, that's better. And also, we want to have the higher deduplication ratio, which means you can save more space. And in order to test our deduplication rewrite algorithm, we implement 8 combinations of the dedupe and restore. The normal one is one with no rewrite. That's the normal dedupe. So we can have a highest deduplication ratio, but maybe its restore performance is the lowest one. Capping is container capping, and 2 is one we proposed, or the one we proposed. FAA is full assembly, which is one type of caching scheme for the restore. And ALAC is another hybrid adaptive caching scheme we developed last year. So we want to see whether with different restore engine, our scheme can perform better or not. And we use 6 different traces from FSL lab. This is the Stony Brook trace. And they are from different servers, and we try to use different backup intervals between them, such that some of the backup will have very diverse chunks, and they were fragmented. Some of them will be very similar, will have less issue. So let's look at the capping and the look-back window LBW. So this is the figure we see. We adjust the parameters and see whether which one can be better in which deduplication ratio. This one is the normal one, which means we don't have the rewrite. So the deduplication ratio can be as high as 15. But the rewrite speed factor is about 1. It's pretty low. And for some companies, maybe they prefer to have a very high restore performance. So let's see, the speed factor is about 3.7, which means when we read out one container, it can restore about 4 or 3.7 megabyte data. For capping case, the deduplication ratio is only about 1.2, which means we nearly have no dedupe. We rewrite 80% or even higher, more chunks in the original data by string. In our case, we can still achieve about 4 deduplication ratio, even if it is much lower than the normal one. So in this case, we save about 75% of the space. But for some companies, maybe they prefer to have very high deduplication ratio, like 14. We can just sacrifice about 7% of the deduplication ratio. In this case, the capping can achieve about 1.27 speed factor. But our one, look-back window, can achieve about 30% higher than capping. So you can see from the low to the high deduplication ratio, our scheme is always better than capping. And this is the overall comparison between the 8 combinations of dedupe and restore. And you can see no matter which restore engine you use, FAA or use ALAC, actually look-back window can achieve the best one in the all 6 traces. And even we look into the backup version, we restore each version of the whole for the backup. And the look-back window can achieve the best one. Sometimes it is close to the FCRC, but sometimes it will be higher than that. So I'll conclude this work and look at the future work. So in this work, we first investigate the advantages and the limitations of capping. And motivated by the limitations of capping, we first propose an improved scheme based on capping called FCRC, and it reduces the container rates and rewrites fewer data chunks comparing with capping, because we set up the boundaries and move the actual capping level. To address the caching issue and the fixed cutting issue of the capping, we propose a new scheme called sliding loopback window-based rewrite scheme. So this one combines FCRC with the caching and also the sliding window. According to the evaluation, the LBW one can achieve the best restore performance comparing with capping and the normal one. So in the future, actually, we want to investigate the restore, the garbage collection process, which considers the restore impact in that. Because in the current garbage collection, what we care most about is how many space we can reclaim in the storage system. But now we may care about, okay, after we regathered some of the chunks in the old containers, how will they affect the future restore performance? That will be a problem. Okay, thanks for listening, and welcome any questions or anything unclear. Thank you.
Questions? I have a question. If I understand correctly, your evaluation was a simulation, is that right?
Yeah, we use a trace to do the simulation of the dedupe and restore process.
Yeah, so backup systems typically put a lot of effort into trying to get some sequentiality. Did you make any attempts to consider the effect of your method upon disk seek times, or did you just look at total amount of data written?
Actually, what we did is we tried to exclude the platform dependency. We evaluate the speed factor, which is we count how many container reads happens during the restore. So like if you have a faster storage system like SSD or have some high spinning speed HDD, the I/O time will be shorter or uses array. But if you have some old disk, the I/O time will be larger. But for the container rates, if you decide the deduplication and the restore engine, you will have the exactly same container rates. So that's why we use the container rates to evaluate that. But yes, actually it is depends on how fast that will be to do the I/O.
Do you have any feel for how random the container reads? Were they going to be random or were they going to be sequential?
Actually, we know usually for the companies like the EMC or Veritas, they use the container size like 4 megabytes or 8 megabytes or larger. So those I/O time will be much larger than the seeking time. So I think we can exclude the disk seeking time in the container rates, but the story will be different if we use the SSD, because that's a random speed is compatible with the sequential speed. We may have a smaller containers, or we may have a different design for the restore.
Okay. Any other questions? Okay, don't go away after we thank the speaker.
Okay, thank you.